An engineering project from the generation to the operation of a plant or machine is generally composed of the following four main phases: planning and configuring, implementation and module test, testing and commissioning, operation and maintenance. The commissioning staff receives the plant software from the project planner or the programmer and must commission the plant safely, efficiently and in due time. The Simatic software gives you optimum support in the testing and commissioning phase with practical testing tools and diagnostics functions. We show you the commissioning process for a plant component as an example and introduce you to the Simatic Manager functions. The commissioning process can be divided into several activity phases in which various testing and commissioning functions are used. During the visual hardware check, completeness and installation of the automation devices are checked and subsequently switched on. The display elements on the modules give you the initial diagnostic information. While commissioning the hardware of the automation devices, it is mainly the parameters and wiring of the modules that are tested using the editor of hardware configuration. In the software commissioning phase, the functions of the user program are tested with the support of the Simatic Manager. In the following, we give you some examples of how to make integration testing and commissioning simple and efficient using the convenient tools. The core area of hardware commissioning is the provision of the automation components with the correct parameters. Furthermore, this phase comprises wiring and signal testing of the process I/O. Normally, the hardware configuration is already generated by the programmer in the implementation phase. However, it can also be corrected or supplemented online during commissioning. Our first commissioning task involves establishing a connection to these two automation devices. The programming device is connected at the Profibus, and the Profibus station addresses of the automation devices have been set according to the plant configuration. After switching on the supply voltage, the LEDs at the front of the CPU indicate the operating mode. The power is on and the CPU is in stop mode. The Accessible Nodes function of the Simatic Manager shows us all the modules accessible at the bus system and their addresses. This gives you a quick overview of which bus stations are already accessible with a programming device. This allows you to easily trace a faulty station configuration and correct it. For loading the given hardware parameters and configurations into the CPU, we open our project in the Simatic Manager, select the station and open the configuration by clicking the hardware icon. The editor of the hardware configuration shows the rack with the modules in the upper window and the detailed information of the modules used in the lower window. Here you can, if necessary, make changes to the parameters or the configuration via the integrated hardware catalog, such as exchanging or adding modules. The transmission of the configuration data from the programming device to the CPU is triggered with the Download to Module button. After switching on, during the startup, the CPU compares the configured setpoint configuration with the actual configuration. In our example, the CPU is programmed to immediately change to stop mode if there is any deviation. In this case, it is a definite indicator that the actual hardware setup differs from that specified by the project planner. With its detailed diagnostics options, the Simatic Manager shows a quick overview of the causes of the CPU stop and subsequently offers you a detailed error analysis. In the window for diagnostic interrupts, you see that the stop cause is a configuration error of channels 0 and 1. From our configuration documents, we know that the connected sensor supplies a current value of 4 to 20 milliamperes. For channels 0 and 1, the measured range plus/minus 10 volts is the wrong default setting. In the offline project, we correct the measured range, save and compile the change configuration. Subsequently, we retransfer the configuration and start the CPU. The CPU remains in run mode and there is no longer a diagnostic interrupt. The mechanism for loading and testing the hardware configuration is the same for all automation devices, and therefore also applies to the Simatic S7-400 of our example. In this early phase of commissioning, the Simatic Manager supports you in assuring a correct hardware configuration. The now customized configuration data provides us with the correct module rack setup in the editor. For commissioning the user program later on, it is absolutely necessary that the signal path, for example from the encoder to the CPU, corresponds to the wiring plans. Wiring and signal testing for the process I/O is performed now, unless already done during installation of the machine or plant. The hardware configuration editor provides you with the easily operable signal test function, which you can also use without user program. Thousands of signals, as occurring in complex plants, can be checked quickly and reliably. We select the digital module and open the dialog for the input signals of the module via the menu item PLC, Monitor, Modify. We select the monitoring mode and can now monitor the switching operation in the plant directly from the programming device. This enables you to check the signal path, for example from a mechanical N-position switch over the module up to the process image input and output table of the CPU. In the same manner, we can also follow the signal path at the outputs. Before directly controlling the outputs, please ensure that, as a result, dangerous states cannot occur in the plant. We insert the value true into the modify value of the output operand. By pressing the modify value button, we set the output and control, for example, a relay of the plant. After terminating signal testing, you have a verified hardware with tested I/O signals. The requirements for commissioning the user program are now fulfilled. The next step is software commissioning, which starts with loading the user program into the controller. This requires the programming device to be online and the CPU to be in stop mode. We open the offline project, which is located on the hard disk of the programming device, and select the station as well as the block container. The block container contains all runnable blocks of the user program. Pressing the Download to Target System button, we now transmit all blocks into the user memory of the CPU. If, for example, during later commissioning phases, only a selection of blocks are to be loaded into the CPU, the Simatic Manager gives you the opportunity of viewing the blocks on the programming device in the offline window, and the blocks in the CPU memory in the online window. With drag and drop, you drag the desired blocks from the offline window to the online window of the CPU and perform the selective load procedure. To continue commissioning the software, please ensure that no dangerous machine or plant states can occur and switch the CPU to run mode. Select the dialog for the operating mode via the Target System menu and start the CPU via mouse click. If the current operating mode changes to run, you can then start testing the functions. If the CPU remains in stop mode, the diagnostic buffer gives you specific information on the cause of the error. The diagnostic buffer provides one of the most important aids to system diagnostics. It can be used for reliably diagnosing and localizing errors in the program, and also the hardware during the commissioning phase as well as later plant operation. The diagnostic buffer is located in the system memory of the CPU and can be read any time with the Simatic manager. In the diagnostic buffer, which is designed as a ring buffer, all important events are saved. For instance, module failures, operating mode transitions of the CPU, or, for example, errors in the user program leading to stop mode. If during commissioning the CPU changes to stop mode, the cause of this will be given to you in the diagnostic buffer, which you access in the Simatic manager via the module information of the CPU. In the displayed information status window of the CPU, you select the Diagnostic Buffer tab. The stop message is given at the top of the event list. Below, you see the message with the error that caused the stop. In the lower window, the Simatic manager gives you further information on the error. In our case, the diagnostics entry shows you the failure of the Profibus station number 3. The cause of the stop is removed by switching on the Profibus station and restarting the CPU. If, as in our next example, the error is caused by the user program, for example, access to a non-existing module address, then you can jump directly to the faulty block. The diagnostic buffer thus enables you to directly and effectively find the error and to remove it. The stop cause of the faulty I/O access is, in our example, directly removed in the block online, so that after restart, the CPU is now in run mode and runs without errors. The successfully corrected block should finally be transmitted from the CPU to the offline project. The user program was loaded onto the target system and is now processed in real time. Checking and, if necessary, correcting the program logic is the next step. On paper, a program logic can be followed very well. However, the real dynamic run behavior of a user program shows only in real-time operation. The Simatic manager provides an excellent test function for this, the program status. Initially, the first main function is monitoring the program run. With the second main function, controlling, you actively engage with the program run. We show you the application in the programming language ladder diagram, and we start with monitoring a block. We open the monitored block directly in the user memory of the CPU via double-click in the online window. The program editor is automatically opened in this display mode. You activate the program status function via the monitoring button in the toolbar. In the program status, the editor constitutes the active binary program flow with a selectable color, green in this example, and shows the current signal status of the operands. If signal status and signal flow change, you will recognize this immediately in a change of color. This makes it very easy to recognize the program status and to trace the program logic quickly and simply. In the program status, parallel to monitoring the program run, you can additionally modify binary inputs and outputs as well as memory bits directly. This intervention has a direct impact on the program run and enables dynamic testing of all kinds of different program states. We show you two ways of controlling the operands. For control at contact, you first mark the operands in the symbol table, which is necessary for the intended test scenario. This promotes clarity in the later test mode. If the control at contact function has been selected and the program status activated, only the buttons for the marked operands are displayed. Clicking the button changes the value of the operand. Using the pre-selection via the symbol table effectively prevents unintended modification of operands which are not part of the test. Another means of direct modification is changing the status of an operand with the commands modify to 0 or modify to 1. Both versions have advantages. The control at contact function enables you to process even extensive test scenarios. Direct operand modifying is suitable for testing individual signal changes and their effect immediately and quickly. Naturally, the program status functions monitoring and modifying are also available for you in the language's function block diagram and statement list. In the programming language statement list, further language-specific functions are offered, such as the display of logic operation results or register contents of the Simatic Manager. In the preceding section, you monitored and controlled individual operands locally within a block. Using the global variable table, you can now also perform this on any other block and this way control the entire user program. An elegant method of preparing several test scenarios is the individual generation of different variable tables. These tables can be generated in the implementation phase and saved in the offline project. You have the option of commissioning individual machines, plant components, or also compiling individual variables for certain commissioning sections. This enables you to fix planned test processes in a reproducible manner. This table can later also be used for servicing and maintenance purposes. Insertable comments and the display of the symbolic names provide additional information on the individual operands. The display columns can be adjusted via the View menu. Additionally, you can also define conditions for reading and writing the variable values. In order to work with a variable table, we switch it online with the Monitor Variable button. Now you can monitor the status values of the listed global variables and define modify values. To do this, you enter the control value true and press the Modify Variable button. The signal change is directly displayed in the status value column, which in online mode displays the current signal status. An example will now show you how to combine the test functions variable table and program status in order to achieve the optimal overview in the testing phase. We activate the program status, which shows us the logic operation for operating a pump, and control the switch on via the variable table. The effects can be immediately observed in the program status. The pump output is activated. If against all expectations the pump switches off, the missing conditions can be immediately recognized in the colorized signal flow. With a variable table, you cannot only do monitoring and modifying, but also forcing. In the initial commissioning phase, for example, this function enables you to set still missing input or output signals to a fixed value, such as permanently switching on a pump independent of the program logic operations. This, as opposed to modifying with variable tables, enables you to define signal or variable values independently of the program sequence. The resulting advantages are: the program code does not need to be changed. No hardware jumpers in the wiring are necessary. The forced values are stored in a table and are therefore comprehensible. The forced values are marked in the program status with a symbol. In the project opened in the Simatic Manager, you select a predefined variable table and open it. You mark the parameters to be transferred to the force table. The menu command Display Force Values displays the force table valid for the CPU, and the selected variables are immediately transferred to the table with their control values. After activation, the CPU permanently executes the force job and indicates this at the respective operand as a force symbol. The status bar contains an indicator for the activated force operation. But the CPU also indicates this operating mode via a force LED. To provide you with information of forced variables at any time, these are marked online with a symbol in the program status or in the variable tables. So it is clear which variable values are predefined independent of the user program, so that misunderstandings can be effectively avoided. In large software projects, it is often difficult to keep track of the complex program structure or the numbers of used variables. The Simatic Manager supports you in this with the option of generating reference lists. On demand, the Simatic Manager compiles the desired overview compactly in the form of lists. The reference data most important in practice are program structure, assignment of variables, and cross-references of variables. The display of this data can be defined individually by means of filter settings. The program structure list shows the call hierarchy of the used program blocks within the user program. This enables you to understand and trace program sequences in the real plant during commissioning more easily. The assignment plan shows you which inputs, outputs, memory bits, times and counters in the program have been assigned or are still free. This helps you to avoid accidental double assignment of operands, for example at program changes. The cross-reference list shows you how and at which locations in the user program certain operands are used. This enables you to quickly find used operands in the program blocks. The cross-reference list, as well as the program structure list, enable you to quickly and conveniently jump directly to the location of the operand or block and make changes in the program editor. The reference lists are a powerful tool for better understanding the plant or machine intended for commissioning. This effectively helps eliminate misunderstandings and avoid errors due to inconsistent changes in the program or at the variables. Beyond the displayed main functions, the Simatic Manager provides you with further testing and commissioning functions. In the following, we will give you a brief overview. The single-step processing function, for example, with which you can edit each individual program instruction step by step. The current program status is displayed, and you can additionally monitor the variables in the form of variable tables. This combination of the testing functions helps you to understand even the most complex algorithms of a block, in order to intervene at the right location in case of an error. Last of all, we introduce you to the Compare Blocks function, which provides easy and safe merging between the online program in the CPU and the offline project on your programming device. In the detailed comparison, the program differences are listed, and in the program editor, the corresponding program locations are compared. A program correction can be performed immediately. This enables you to synchronize the different program states. Inconsistencies between the development level and the program code currently on the CPU are prevented this way. The test functions provided by the Simatic Manager enable cost-effective and reliable commissioning on time. In summary, this means quick and reliable setting of parameters with the editor of the hardware configuration, convenient commissioning by means of simple loading of changed program blocks during running operation, clear and targeted analysis of system or process failures by means of the Diagnostic Buffer, structured and convenient program model test by means of monitoring, modifying, and force functions, practice-relevant support by means of extensive information functions such as program structure, cross-reference list, or assignment list using reference lists.